Hello, 307 students, and thank you so much for joining me for this video. So a lot of the content of this video should be review for most of you from 306 and also from other stats classes that you've taken. But this video is going to review Pearson correlations. So we conduct a Pearson correlation when we are looking for a relationship between two continuous variables. So for example, most of what we have discussed this semester has been t-tests and ANOVAs, right? So we've talked about how we would utilize t-tests and ANOVAs in cases where we have either a between subjects or a within subjects design. Okay, but generally the criteria for both t-tests and ANOVAs is that we have a categorical variable, independent variable, and a continuous dependent variable, right? And there's also something that if you took 306 with me during fall or spring semester, you learned about a test, a statistical test known as a chi-square test, and specifically a two-way chi-square test in which we have two categorical variables, right? Well, by process of elimination, right? When do we use a Pearson correlation? We use it when we have two continuous variables and we want to see if they are related in some way, right? So I have a helpful little table there for you that kind of creates a reference sheet. So, like I said, when you have a two variables that are both continuous, then you would utilize a Pearson correlation. Right? So when would you use a Pearson correlation? Well, you would use it when you're interested in figuring out if there's a relationship between two continuous variables, right? So for example, you might be interested in whether or not ice cream sales increase as the temperature increases, right? So in that case, whenever we talk about correlation, we have a predictor variable, which is essentially the same thing as an independent variable would be in an experiment, and a criterion variable, which you guessed it, is sort of the same thing as a dependent variable, right? So the predictor variable is whatever variable you think might have the potential to be a causal variable, right? And I say potential because, of course, one of the very first things you learned all the way back in intro psych, right, is that correlation does not equal causation, right? But whatever variable you think may be driving the relationship is the predictor, and the criterion is the variable that you believe might be affected, right? So again, ice cream would be the predictor, and the criterion would be rising temperatures in the summer, right? Similarly, you might be interested in investigating whether there's a relationship between fuel efficiency and horsepower, right? But let's talk about exactly what a correlation in those cases would mean. Okay, so whenever we calculate a Pearson R, that value can range from -1 to +1, right? And the strength of the correlation is indexed by the absolute value of that number, right? So generally speaking, right, we would assume that the closer one gets to 1, the stronger the correlation, right? So obviously, right, the number itself is going to indicate the strength of the relationship, okay? And if r equals 0, then we would assume the variables are not at all related, right? Whereas an r of positive or negative 1 means that the variables are perfectly related, right? And in a sense, what that tells us is that if we know the value of x, we automatically know the value of y, right? And the direction of the correlation is indicated by the negative or positive sign, right? So if your Pearson R is greater than 0, okay, that means as x increases, y increases, right? So that is what's called a direct relationship, right? So for example, a positive correlation might be as hours studying increases, grades on exams also increase, or GPA also increases, right? Whereas if your Pearson R is less than 0, meaning it's negative, that means there's an inverse relationship. So as variable x increases, y does the opposite, or vice versa, right? And kind of a classic example of a negative correlation is between depression and self-esteem, right? So as your depression increases, okay, your self-esteem decreases, okay? And when we want to graphically represent a correlation, we use something known as a scatter plot, okay, where variable x is plotted on the x-axis, variable y is plotted on the y-axis, and each circle in the graph corresponds to an observation or a data point, okay? And whether the correlation is positive or negative, if the correlation is significant, then the cluster of dots can be fitted with a line, or another way of thinking about it is that it's linear, right? So that it has a very linear or line-like appearance. Whereas if there's not a relationship between variable x and variable y, then there's kind of just this random assortment of dots that doesn't have any sort of discernible pattern, right? But now let's get to that sort of golden rule that you all have been taught, that correlation does not equal causation, or does not imply causation, right? So really the crux of the issue is that unlike experiments where we have an independent variable that's hypothesized to be exerting an influence on a dependent variable, and we have things like random assignment, and we have an experimental group and a control group, and we control for extraneous variables, and we take very careful steps to eliminate potential confounding variables. This is not the case with correlational studies, and therefore we cannot conclude that changes in one variable cause change in the other variable. Okay, and that's because there are two possible explanations anytime we have a relationship between variable x and variable y, right? So one of the issues is something called the directionality problem. So we don't know whether changes in x are producing changes in y, or vice versa, right? So remember, I told you that there is a reasonably strong negative correlation between levels of depression and self-esteem. So the more depressed you are, the lower your self-esteem is, right? So we don't know, though, on the basis of that negative or inverse relationship between depression and self-esteem, whether depression causes the negative self-evaluation, or the pessimistic sort of comparison of oneself to others. So we don't know if uh, sadness and generally poor affect causes that negative self evaluation, or if the opposite is true, right? So maybe it's possible that negative evaluation causes low mood and issues with emotional regulation and so forth, right? So we don't know if depression causes low self-esteem or chronically low self-esteem causes symptoms of depression, right? So that's the directionality problem. There's also something known as the third variable problem, right? And that essentially means that if we have a relationship between X and Y, right, it's possible that X is causing changes in Y, or Y is causing changes in X, right? But it's also possible that a third variable is causing that relationship. Okay? So sometimes it's unclear which variable is the independent variable and which is the dependent variable, right? Which is where we get predictor and outcome from, right? So let me show you some classic examples of that illustrate the directionality problem and the third variable problem, right? So again, the directionality problem is it's unclear whether X causes Y or Y causes X, right? So we know that there is a positive correlation between obesity and watching television, right? But we don't know on the basis of this relationship if watching television causes obesity or if obesity causes an increased consumption of television, right? So we could say that watching television increases sedentary behavior, and that causes weights to increase. Or we could say that those who are obese tend to gravitate toward a more sedentary lifestyle, right? We don't know on the basis of that relationship what is the independent variable or the dependent variable, like I said. Another classic example of the third variable problem is the correlation between ice cream sales and homicide, right? So it has been demonstrated that there is a significant positive correlation between ice cream sales and crime, specifically homicide, right? So one explanation is that eating ice cream increases one's propensity for homicidal rage, right? And another explanation could be that engaging in homicidal behavior gives people a hankering for ice cream and other sugary treats, right? But both of those explanations seem kind of ridiculous, right? So there's an obvious third variable there, in that during the summer, right, temperatures increase, and that leads to increased consumption of ice cream and also a shorter fuse, which in a very small select portion of the population might cause violent behavior. Okay? So yeah, so we can't infer any sort of causality because of that, because of those express limitations. Okay? Okay, so I am not going to make you guys do any sort of calculations by hand. For the Pearson correlation, you will do everything in SPSS. But I did want you to see kind of where the information is coming from, so to speak. So again, Pearson R ranges anywhere between -1 and +1, and as R gets further from 0, the relationship gets stronger, right? And we do have um, general guidelines for what constitutes a weak correlation and what constitutes a strong correlation, right? So, for example, in R of less than 0.3 in either direction, negative or positive, is considered to be that we would conclude that there was a weak relationship between X and Y. A Pearson R between 0.3 and 0.5 is considered a moderate relationship. Between 0.5 and 0.07 is a strong relationship. And anything greater than 0.7 is considered a very strong relationship. Okay? So let's look at an example here. Okay, so let's return back to one of the first examples that I gave you. So suppose we wanted to see if there was a significant correlation between GPA, freshman or first year GPA, and the number of hours spent watching TV per week. Okay, so here is our data from a sample of 12 students, and variable X is GPA, and variable Y is number of hours watching TV. Okay, so the null hypothesis is that R is equal to 0, or that there is no relationship between GPA and time spent watching TV, whereas the research hypothesis, or the alternative hypothesis, is that there is a relationship between GPA and time spent watching TV. Okay? So let's suppose we enter this data into SPSS, and you guys will learn how to do this for both correlation and regression when you complete your SPSS tutorial this week. But let's suppose this is what SPSS gives us, right? So we have an R of negative 0.58, and our p-value is less than 0.05, right? So right away, on the basis of that significance value, or that p-value, we can conclude that because it's less than 0.05, there is a significant negative correlation between freshman GPA and how many hours of TV a student watches per week. Okay? And as far as calculating degrees of freedom, it's very easy. Okay? So N is just the number of paired observations, right? Or it's the number of essentially the number of participants in your sample, right? Minus 2, right? So our N is equal to 12, which gives us a degree of freedom of 10. Okay? And again, the sign is negative, which tells us that as freshman GPA increases, the amount of weekly hours watching TV decreases, and vice versa. Okay? Remember, our criterion is that any value of Pearson R between 0.5 and 0.7 is considered a strong relationship. Okay? So we know that there's a relationship between these two variables. Okay? We know it's a strong relationship and it's a inverse relationship, but we still don't know anything about causality or cause and effect. Okay? But I should say that correlational research design often serves as a precursor to experimental design. Okay? So once we identify that there is a relationship between X and Y, then we can design an experiment, like I said, with random assignment and control for extraneous and confounding variables, okay, that allows us to see more about potential causal factors that contribute to this relationship, right? Okay. And like I said, whenever we are doing any sort of correlational analysis, we want to display the results in a scatter plot, right? And like I said, stronger correlations start to look linear, okay, in the sense that they could be fit with a straight line, okay, whereas weak correlations often look like a random assortment of dots with no clear increase or decrease, okay? And this will become relevant in my next video, but one thing to note that I've already mentioned is that as our Pearson R increases, you can more accurately use X to predict Y. Okay? And that's essentially what we will be doing when we talk about regression analyses in my next video. Okay? So thank you so much for watching, and I'll see you in my next video.